As we saw at the end of the last section, when you're counting possible outcomes using the multiplication principle, it's fairly common to get expressions like 5 times 4 times 3 times 2 times 1, where you start off with the number 5 and everything that you multiply by thereafter is reduced by 1. This happens so often that we come up with a name for this. We come up with a notation for this. And here's our definition. So for any natural number n, we're going to define this expression called n factorial. So it's n with an exclamation mark after it. And n factorial is defined to be the number n times n minus 1, so you subtract 1 from n, times n minus 2, so subtract 2 from n, lower it by 2. So n times n minus 1 times n minus 2 times n minus 3. Keep going until you finally reduce down to 3, 2, and 1. So it's the number n, the natural number n, times all of the natural numbers that are less than it. Right? And just to make our formulas work out, we want them to make sort of sense if I plug in 0. So we're just going to make this definition. We're going to plug in, we're going to define 0 factorial to always equal 1. Alright, so for example, something like 5 factorial, well, by our definition, 5 factorial would be the expression I just said, 5 times 4 times 3 times 2 times 1. So you'd work this out. 5 factorial is 5 times 4 is 20, times 3 is 60, times 2 is 120. Alright, so this is all the factorial is. It's the number times all of the natural numbers that are less than it. Let's do another one. How about, so I'll call this example A. We'll do B. What if I do, say, 7 factorial divided by 5 factorial? Right, well, what does this represent? This is 7 factorial 7 times 6 times 5 times 4 times 3 times 2 times 1. And this is divided by 5 factorial, which is 5 times 4 times 3 times 2 times 1. And you'll notice a lot of stuff cancels here. You'll notice that 5 cancels with 5, 4 cancels with 4, 3 cancels with 3, 2 with 2, and 1 with 1. So this is just 7 times 6, which is 42. But I'm never again going to write out the full factorial, because there's a much faster way to do this cancellation. So, or I could have just said 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. But what is 5 times 4 times 3 times 2 times 1? Well, that's just 5 factorial. Right, and what do I have on the bottom? I still have this expression 5 factorial on the bottom. And now instead of writing out the full factorial, now I can just cancel them, because it's 5 factorial on the top, 5 factorial on the bottom, and they cancel, and once again, I get 42. So this is really common. We'll often see expressions where we've got ratios of factorials, and to cancel them, you would do this trick. All right, so you would count out the top or the bottom, count out the bigger factorial until you get down to the smaller factorial, and then stop. So here I had 7 times 6 times, I got to the smaller factorial times 5, and I just wrote that as a factorial, and then we canceled them. All right, so that's really common. Let's do another example. How about example C? So 9 factorial over 8 factorial. And once again, I'm going to do the exact same trick here. So I'm going to count out until I get to the smaller number. So 9 factorial is 9 times 8 times 7 times 6 times 5, but just factorial over 8 factorial. So those cancel, and this works out to just be 9. And we'll just do one more. D, 52 factorial over 5 factorial times 47 factorial. And you can do this, right? This is just one number, 5 factorial times another number, 47 factorial, and I'm multiplying them together. Well, let's start canceling. I'm going to expand this 52 factorial until I get to the smaller number here, 47. So this is 52 times 51 times 50 times 49 times 48 times 47 factorial over 5 factorial times 47 factorial. The 47 factorials cancel. And let's expand this. Instead of writing 5 factorial, let me expand that. Let me write that as 5 times 4 times 3 times 2 times 1. And of course there's more cancellation I could do here. For example, I've got, what could I do? I could say 5 goes into 50 10 times, so I could cancel this and replace that with a 10. 4 goes into 48 12 times, so I could cancel 48 over 4 and replace that with a 12. 3 goes into, what else do I have? 51, that's 17 times, and 52 is divisible by 2, that's 26. And you would compute this product, 26 times 17 times 10 times 49 times 12. But when the numbers get this big, you really can just plug everything into a calculator. Your calculator should have a factorial function, by the way, so you would just type in 47 factorial, and it'll tell you what it is. But this works out too, if you simplify this, or compute this, is 2,598,960. Alright, so being able to work with factorials like this, being able to cancel factorials in this way, sort of counting out until you get to the smaller one and then canceling, is a really important skill. And there's actually just one more thing I want to point out, which is that you should know that it's sort of a squaring function. You take x squared. That grows really quickly. Exponential functions like e to the x or 2 to the x or whatever, those grow even faster. Exponential functions grow really quickly. Factorials grow extremely quickly, even faster than factorials. For example, we saw 5 factorial was 120. Keep computing them. Here's 10 factorial. If I compute 10 factorial, this is 3,628,800. 15 factorial, if you compute this, this is now up in the trillions. This is now 1,307,674,368,000, and that's it. So I'm plugging in very small numbers into these factorial functions. 5 factorial, 120, 10 factorial, 10 is a small number, plug it in, you're in the millions. Plug in 15, now you're up to the trillions. Take something, just for fun, take something like 70, plug in 70 factorial into your calculator, see what happens. These numbers are absolutely gargantuan. Factorials grow very, very, very quickly. Alright, so getting back into counting, we've got permutations and combinations in this section, and a permutation is just a rearrangement of the objects. Alright, so a permutation of a set of distinct objects is an arrangement of the objects in a specific order without repetition. So it's just asking, if I have this set of objects, how many different ways can I rearrange them? Or rather, a permutation is a specific rearrangement. Alright, so what we often are looking for is how many different permutations are there. For example, I've got 4 paintings are to be arranged from left to right on a wall. How many permutations are there? How many different ways can I order my paintings? And it turns out this is something you already know how to solve. It's just the multiplication principle in action, right? I've got 4 different paintings. And the question is, how many different ways can I order them? Well, for the first spot, I've got 4 choices of paintings to hang there. For the next spot, I've already hung one, so now I'm down to 3 paintings that I can choose to hang there. Now I've already hung 2 paintings, I'm down to, for the third spot, I've got 2 choices of paintings that I can hang there. And once I've chosen that one, I've just got a single choice of painting that I can hang in that last spot. So the answer is there's 4 times 3 times 2 times 1, or 4 factorial, which is, what is this, 12 times 2 is 24, 4 factorial, or 24 different permutations. And so it's just a multiplication principle in action. If you want to come up with all different orderings, you'd say, well, for the first choice, I've got 4 choices, then 3 different paintings, and 2 times 1, multiply them all together. So let's state this is a theorem. This is what always happens. If you have n objects and you want to know how many different permutations are there of n objects, the answer is n factorial. So here's our first theorem, and I'm actually stating this for two reasons. One is it's a useful observation to make. So the number of permutations of n objects without a repetition is n factorial. But I'm introducing some notation here as well. So the number of permutations of n objects, we're going to denote this with this symbol or this expression. The n's here are subscripts, so it's n, usually read as npn, with n as a subscript on both sides. A little bit of strange notation, but you'll see why I'm using this in a second. So here's the next question. What if I want to do something else with my paintings? So what if we only want to form arrangements using two of the four paintings? All right, so now I'm not forming permutations of all four. I'm just taking two of the paintings, and then here's what I should say. So I really only have two choices now, right? I've got two painting slots, and the question is how many different arrangements can I form now just using two of them at a time? Well, for the first slot, for the painting on the left, I've got four choices of paintings that I could put here, and for the painting on the right, well, I've used one of them. So now I've got three choices of painting there. So the answer in this case is, if I'm forming arrangements using two, it's 4 times 3. But I'm going to write this in a slightly different way. 4 times 3, I'm going to write this as, you can compute this by the way, this is just 12. The answer is 12 different arrangements. But I'm going to write this as 4 times 3 times 2 times 1 divided by 2 times 1, so they cancel, or 4 factorial over 2 factorial. Why am I doing this? Well, because our theorem is going to say that if we're forming arrangements of r objects out of n total, then the total number of arrangements is going to be n factorial over n minus r factorial. So you can even go a little bit further here. This is 4 factorial over 4 minus 2 factorial is what the formula is really going to say is how we're going to compute this. Okay, so the last example, the answer was 12. I was just sort of rewriting it in that funny form to show that it matches up with our next theorem, which says that if we're doing something like this, if I'm not permuting all n distinct objects, but I'm permuting r objects taken from a set of n, then the number of permutations I have there is given by n factorial over n minus r factorial, where r is some number between 0 and n, some natural number between 0 and n. And the notation we'll use here, coming back to our npn stuff, is npr. Alright, so the n tells you how many total objects you have, r tells you how many you're actually using or permuting. And there's a lot of different notation for this in the literature, so this is what we'll go with, but you'll often see something like pnr, or p superscript n subscript r there, or even p of n and r. So you'll see all sorts of different notation. But this is what you usually see on a calculator, this expression here. Alright, so let's just jump straight into examples. Alright, so we already did an example like this. We have 4 paintings. We want to know how many permutations there are if we take 2 of them at a time. So no real world interpretation here. It's just a question of find the number of permutations of 30 objects taken 4 at a time. Well, what we're trying to compute is 30p4. Right, 30 total objects, we're permuting 4 of them at a time. So plug this into our formula. It's n factorial, so we've got 30 factorial over n minus r factorial, so 30 minus 4 factorial. So this is 30 factorial over 26 factorial. And now this is why in the beginning of this section I pointed out that it's really useful to be able to work with factorials and know how to cancel and whatnot, because these types of expressions come up all the time. So we're just going to write this as 30 times 29 times 28 times 27 times, now we're finally down to 26, so we'll stop here, 26 factorial over 26 factorial. Those guys cancel. This looks like a pretty big number. I would just plug this into a calculator and I get 657,720 different permutations. So as long as you understand what this expression is and how to apply it, these problems aren't particularly difficult. Using this function or using this expression, this formula, can be really nice when the numbers are large and messy. But notice that you'll get the same exact result if you just think in terms of events and how many different possibilities there are for each event, as we've been doing, right? If you just want to think of, I've got 4 choices. For the first choice, I've got 30 objects to choose from. For the second choice, I've got 29 objects to choose from. Third choice, I've got 28 objects. Fourth choice, I now have 27 objects to choose from. So how many different possibilities are there? Well, it's the product of all of these, which is exactly what we just counted. So if you want to keep thinking in terms of this is totally fine. To be totally frank with you, this is quite often how I think about permutations. But understanding this formula, where it comes from, can be useful in what we're about to do. So we're going to look at no longer permutations, but combinations. We've got a slightly different problem now. So suppose that instead of arranging the 4 paintings on the wall, suppose we want to donate 3 paintings to a museum. The question is, how many ways can we select 3 paintings from the 4? And what I want you to notice here is that order doesn't matter. Right? It doesn't matter if I choose 3 paintings and I take a different permutation of the 3 paintings. That's not a different selection, right? So if I computed 4p3, this isn't what I'm looking for, right? This is giving me the total number of permutations of 3 paintings chosen from 4. But what I want to observe is that this is a product of 2 different events. The first event is the number of ways that I can choose 3 paintings from 4. Right, so number of ways to choose 3 paintings. So the first thing I do is I choose 3 paintings, right? And when I choose 3 paintings here, the number of ways that I can choose it is this expression. And then that's multiplied by the number of ways that I can permute the 3 paintings. Number of ways to permute the choice. And that gives us this actual expression. We know what this comes out to be. We know this comes out to be 4 factorial over 4 minus 3 factorial, which is just 4 factorial over 1, sorry, which is 24. But I want to come back to this intermediate step, right? We usually jump over this and we jump straight into, there's our formula. But there's sort of this intermediate step. When I'm finding how many ways can I permute 3 objects chosen from 4, well, I'm doing 2 things. One is I'm taking a choice. I'm taking a choice of the 3 paintings, and then I'm permuting them all. So the number of total possible permutations is the number of ways to choose the 3 paintings times the number of ways to permute the choice that you have. So this is what I'm really looking for, right? I'm looking for, the question is asking, how many ways can I choose 3 paintings from the 4? And we're going to give this some notation. This will be, this is what we'll call 4 choose 3, so 4c3. And how many ways can I permute 3 different objects? 3 factorial, right? And we already know that this equals, we've figured it out. The number of permutations of 3 objects chosen from 4 is 24. Well, yeah. Number of ways to permute, number of permutations that you have when you're choosing 3 objects from 4. Anyway, so what I have is that the number of choices, 4 choose 3, is 24 over 3 factorial, which comes out to what? 3 factorial is 6, so this is 24 over 6, or 4. Alright, so this is the answer. There's 4 ways to choose 3 paintings from a set of 4. Shouldn't come as a surprise, right? If you're choosing 3 paintings from a set of 4, really what you're doing is you're choosing which painting to leave out. Since you're only leaving 1 painting out each time, then there's 4 different choices for how many paintings to leave out. So the answer is, of course, obviously 4. But the way we found this is by isolating this expression that's part of this permutation combination. So the observation I'm going to make is that if I want to compute this in general, I can actually express this in terms of the permutations divided by the number of possible ways to permute them. Let me make this precise. I'm just going to write down a formula now for this expression forevermore so we don't have to go through this process. Alright, so I feel like I might have been going off on a bit of a tangent there with that explanation in the last example, but that's okay. We'll just jump straight into the formula. The number of combinations of n distinct objects taken r at a time. So last time we were trying to choose 3 objects from 4. The number of combinations is denoted in NCR, and as we saw in the last example, NCR is actually NPR divided by r factorial. So if you replace NPR with the formula for NPR, that's n factorial over n minus r factorial times r factorial in the denominator. So there's the formula, and then once again we have alternate notation for this. You'll often see same thing, CNR, or C superscript n subscript r, or C of nr. But there's one that's really common that I like personally. It's like this, nr with round sort of matrix brackets on either side, and this is read as n choose r. Which is very descriptive. It's saying counts the number of ways that given n objects you can choose r from them. So what's the difference? What's the difference between these two expressions? NCR is the number of combinations. And the most important point here is that order doesn't matter. When you're looking at combinations, you don't care about the order of the objects that you get, right? For example, ABC and BCA, those are different permutations of the 3 letters ABC. But as far as combinations go, they're the same combination because I no longer care about order. All I care about is that I have the same combination of 3 letters. All right, so combinations, and the point is order does not matter. Meanwhile, permutations and PR, this is the number of permutations. And the important point is that order does matter. Alright, so when you're asking yourself in these problems, which one should I be using? Am I counting number of permutations or combinations? Ask yourself if the order matters. If it does, then you're counting permutations. If it doesn't, then it's combinations. Here's a typical example. From a committee of 12 people, 2 questions here. 1, how many ways can we choose a chairperson, a vice chairperson, a secretary, and a treasurer, assuming one person cannot hold more than one position? And B, how many ways can we choose a subcommittee of 4 people? Let's go to the second one. The second one is I think, a little bit easier. How many ways can we choose a subcommittee of 4 people? Well, notice in this case, order doesn't matter. The order of the 4 people you choose doesn't matter. I'm just asking, from 12 people, how many ways can I choose 4 people? So this is a combination question. I'm asking, from 12 people, how many ways can I choose 4? So I'm computing 12C4, or 12 choose 4, if you like this notation, which I personally do. And now we'll just go straight to our formula, right? 12 choose 4 is 12 factorial over 4 factorial times 12 minus 4 factorial, or 12 factorial over 4 factorial times 8 factorial. And you could plug this into a calculator now if you want, but I'll try and simplify some of it by hand. This is 12 times 11 times 10 times 9 times 8 factorial over 4 times 3 times 2 times 1 times 8 factorial. The 8 factorials cancel. 4 times 3 is 12, that cancels with the 12. 2 cancels with the 5, or 10, and I'm left with 5. And what am I left with? I'm left with 5 times 11 times 9. So that's 55 times 9. 55 times 10 is 550, so 55 times 9 is 495. 495 different ways to choose 4 people from 12. By the way, in terms of sets, if you think about this in terms of sets, what am I doing? I've got 12 objects in my set, the set of 12 people. This is asking how many different 4-element subsets are there. Right, this is what combinations are doing. It's how many different 4-element subsets are there of 12, which in this case is 495. So come back to the first question. Here I'm also choosing 4 people, right? I'm choosing 4 people, a chairperson, a vice chairperson, a secretary, and a treasurer. So down here, order didn't matter. This is always up to you to decide, by the way. You have to figure out, am I doing a combination or a permutation? Does order matter or not? But up here in the first problem, order does now matter, right? I'm not just choosing 4 people. I'm choosing 4 people, but then I'm also looking at specific order. I'm saying 1 is going to be the chair, 1 is the vice chair, 1 is the secretary, and 1 is the treasurer. So I'm choosing 4 people, and then I'm looking at all different permutations of those 4. Right, so this is in fact a permutation question because order matters. So we're computing 12p4, which is 12 factorial over 12 minus 4 factorial, or 12 times 11 times 10 times 9 times 8 factorial over 8 factorial. That's a pretty big number. This works out to be 1,880. Right? Should expect it to be bigger because I'm doing 2 things here. I'm taking how many ways can I choose 4 people, and then once I've got my choice of 4, how many ways can I rearrange them all? How many ways can I permute them all into chairs, vice chairs, secretaries, and treasurers? Once again, though, I want to point out that this is this old school method that we were using of just saying, well, I've got 12 choices for the chair, 11 for the vice chair, 10 for the secretary, and 9 for the treasurer. Multiplying them all together gives you the exact same answer. All right, but the trick is to figure out, does order matter or not? Am I doing a combination or a permutation? So we'll do another example. All right, next up, a sports team has 5 distinct positions. Out of 8 players total, how many starting teams are possible? So how many different ways can we choose starting teams from the 8 players if A, the distinct positions are taken into consideration? All right, so I don't know what these positions are. It's just a generic sports team, but I've got 5 positions, and I have to choose a player from 8 total for each position. So clearly order is mattering here, right? It matters who I put in position 1, position 2, position 3. That will give me a different a different starting lineup than if I take the same 5 players, but I put them in different starting positions, right? So we're computing permutations of 8 players, choosing 5 of them. So now we just go straight to our formula. This will be 8 factorial over 8 minus 5 factorial, which is 8 factorial over 3 factorial. Alright, so you compute this, I guess we could maybe do it by hand. The number looks pretty big here, but this is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, or 3 factorial, over 3 factorial. Those cancel. And I just have to compute this product, 8 times 7 times 6 times 5 times 4. It's a pretty big number. This is 6,720 different permutations, different starting teams. Once again, I want to remind you that because order matters here, you could have gone with this old-fashioned approach of just, here's position 1, I've got 8 choices, position 2, I've got 7, 6, 5, 4, and get the exact same expression. Okay. But now B, the distinct positions are not taken into consideration. So now I'm not going to consider it a different lineup if I have the same 5 players but in different positions. I no longer care about the positions. It's just how many ways can I choose 5 players from 8 players. So we're doing a combination. We're asking what is 8 choose 5? Right, well, we go to our formula. This is 8 factorial over 5 factorial times 8 minus 5 factorial. So that's 8 factorial over 5 factorial, 3 factorial. This one you don't need a calculator, you can do this by hand. So this is 8 times 7 times 6 times 5 times 4 times 3, 3 factorial. I don't know, there's really no point stopping there, let's just keep going. 3 times 2 times 1 over, and we'll just expand the whole bottom. 5 times 4 times 3 times 2 times 1, it's 5 factorial. 3 factorial is times 3 times 2 times 1. And we'll cancel as much as we can. 3's cancel with 3's, 2's with 2's. I've got 5 and 5, 4 and 4. 3 times 2 is 6, those cancel with that 6. And I'm just left with 8 times 7, which is 56. So from a pool of 8 players, there's 56 different ways to choose 5 players. Now we're jumping into something distinctly more difficult than what we've been doing so far. I don't have enough space, so I'm just going to have to erase all of this. Alright, so here we have the distinct positions are not taken into consideration, but one of Scott or Terrence, but not both, has to start. So there's actually 2 different events happening here, right? I have my first player, and then I have the rest of them. Right? And this guy, I have to choose either Scott or Terrence. So how many different choices do I have for this first event? I've got 2 choices, right? Either Scott or Terrence. So I've got 2 different choices there. And then I choose the remaining 4 players. So the second event, how many different outcomes are possible here? Well, I have 7 players left that I'm choosing 4 of them from. Oh wait. 1 of Scott or Terrence, but not both. So I'm actually not allowed to start both of them. So from my 8 players, I've removed 2. 1 that starts and 1 that's on the bench. So I'm actually choosing 4 players from the 6 remaining players. So I have 2 events here, and in comes the multiplication principle. right? The total number of possible outcomes is going to be the product of these two numbers. So we're computing 2 times 6 choose 4, 6 factorial over 4 factorial times 6 minus 4 factorial. This is something you'll often have to do, and it makes the problems quite a bit harder, is using the multiplication principle when you have two different choices to make, two different separate choices, and then you have to multiply them together to get the total number of possible outcomes. This 2 looks like it's down there in the denominator or something. But this is so this is 2 times, how am I going to simplify this? Let's just go 6 times 5 times 4 times 3 times 2 times 1. Then I've got 4 factorial, 4 times 3 times 2 times 1. And then 6 minus 4 is 2 factorial, so that's 2 times 1. And we'll just cancel as much as we can. 4, 3, 2, 1, 2. We'll divide that into 3 and make that, or sorry, we'll divide that into 6 and leave that as a 3. So I've got 3 times 5 is 15 times 2 is 30 possible combinations. All right, so it is a product of two different choices. It's first, how many ways can I choose 4 from 6? The 6 players that aren't Scott or Terrence. And then times that by, okay, I then either choose Scott or Terrence for my last position. We'll do another example like this. Counting combinations obviously pops up all the time when you're working with decks of cards. So here's an example from a standard 52 card deck. Question A, how many 5-card hands consist entirely of face cards? So 52 card decks, of course, there's 4 suits, hearts, spades, clubs, and diamonds. So 4 different suits, 13 cards of each suit. The face cards, Jack, Queen, King, and then there's, of course, Ace and 2 through 10. So how many face cards are there? Well, once again, so the face cards are Jack, Queen, and King. So there's 4 Jacks. Let's just count number of face cards really quickly. Number of face cards, 4 Jacks, plus 4 Queens, plus 4 Kings is 12 total face cards. And when I'm constructing a 5-card hand out of face cards, of course the order doesn't matter. It doesn't matter which order I put my cards in. If I rearrange them, it's still the same hand. So how many different 5-card hands are there? Well, this is asking how many ways can I choose 5 cards from a pool of 12 face cards. That way they will all be face cards. Right? So we're just computing 12, choose 5. Use your formula now. This is 12 factorial over 5 factorial times 12 minus 5 factorial, which is 12 factorial over 5 factorial, 7 factorial. And you can compute this by hand or plug it into a calculator. This is 792 possible hands. Alright, well now, second question is a bit more complicated. How many 5-card hands have 3 hearts and 2 spades? Once again, notice that the order doesn't matter here. It doesn't matter which order we put our cards in our hands in. It's still the same hand. But how many have 3 hearts and 2 spades? Well, what I want to do is ask, how many ways can I get 3 hearts? And then multiply it by how many ways can I get 2 spades? Right, remember there's 13 hearts total and 13 spades. In a standard deck there's 13 of each suit. So if I want to ask how many ways can I get three hearts in my hand, well this I'd be choosing 3 from a pool of 13 hearts. How many ways can I get 2 spades? Well, that's asking how many ways can I choose 2 from a pool of 13 spades. And then to get the total number of possible combinations of all of them, Now I have to multiply these two events together. Alright, number of possible ways to get 3 hearts, number of possible ways to get 2 spades, multiply them together, and we'll get our answer. So 13 choose 3 is 13 factorial over 3 factorial times 13 minus 3 factorial times 13 choose 2, 13 factorial over 2 factorial, 13 minus 2 factorial. This looks like it probably simplifies fairly nicely, but once again, not the nicest. Well, let's see what we can do. This is 13 factorial over 3 factorial times 10 factorial times 13 factorial over 2 factorial times 11 factorial. And definitely a lot of stuff is going to cancel here, but if it was me, I would just plug this into a calculator and you will get 22,308. A lot of combinations, right? As far as 52 card decks go, there's often many combinations of different hands. So I think we've done enough examples. Obviously not enough to just watch this video and achieve mastery. This is the type of thing that I highly recommend doing as many practice problems as you can to make sure you really have a grasp on when am I using a combination, when does order not matter, and when am I counting permutations, when does order actually matter. And become really good at this stuff because it's going to be very important down the road as we start doing probability. Thanks.